We've finished up kinematics, and now we're moving on to kinetics. So we'll be starting chapter 13 in the textbook. Recall that we started on the right side of the F equals ma equation by studying the geometry of motion without thinking about the forces that cause it. Now we'll start looking at the forces, and we'll spend more time with Newton's second law of motion. But first, start by recalling the first law of motion that says an object will remain in its original state of motion, either at rest or moving at a constant velocity, if there is no unbalanced force acting on it. Such objects are in a state of equilibrium. This was the focus of the statics course. The second law says that the acceleration of an object is proportional to the resultant force acting on it, and it's in the same direction as the resultant force. The equation of motion is then sigma F equals ma. We will work a great deal with this equation. The third law says that the forces of action and reaction between two objects are equal, collinear, and opposite in direction. Otherwise said, if A exerts a force on B, then B exerts an equal and opposite force on A. Moreover, the forces act along the line joining A and B, and these forces may be attractive or repulsive. Moreover, forces may be divided into two categories: contact forces and forces exerted at a distance. Contact forces include collisions between two particles and pulling an object by a rope. Forces exerted at a distance include gravitational attraction and electromagnetic forces. There are a few specific forces that we'll work with a lot in this course, so we'll cover those in greater depth now. The first is friction. Friction is a contact force that always works against the direction of motion. The magnitude of the frictional force is given by F equals mu n, sometimes pronounced fun. Here, mu is the coefficient of friction, which is written as mu sub k if the object is moving. This is the coefficient of kinetic friction. And it's written as mu sub s if the object is at rest. This is the coefficient of static friction. N is the normal force exerted by the surface, but I typically write the normal force as F sub n to distinguish it from the units of newtons. If a spring is part of the system of interest, then the magnitude of its associated force is given by F sub s equals Ks, where K is the spring's stiffness, which is measured as a force per unit length, and S is the amount of stretch or compression, defined as the difference between the deformed length, L, and the undeformed length, L naught, such that S equals L minus L naught. Note that the spring force opposes the direction of S, so be very, very careful with the sign when you're writing the spring force as a vector. We will also work a lot with gravity. Newton's law of gravitation says that if two objects of masses m1 and m2 are a distance r apart, then each attracts the other with a force of magnitude F, acting along the line joining the object's centers of masses. The gravitational attraction forces between any two objects are equal and opposite and have magnitude capital G, m1, m2 over r squared, where capital G is the universal gravitation constant. Assuming the Earth is a spherical body with density that depends only on the radius, then the gravitational attraction of the Earth on an object of mass m is given by Fg hat, where F is the gravitational constant, capital G, times the mass of the Earth times the mass of the object, divided by the square of the distance between the center of the Earth and the object. G hat is a unit vector pointed toward the center of the Earth. If we assume that the object is near the Earth such that its radius from the center of the Earth is approximately equal to the Earth's radius, then the force exerted by the Earth on the object is capital G times the mass of the Earth times the mass of the object divided by the radius of the Earth squared. If we define small g to be the gravitational constant times the mass of the Earth divided by the radius of the Earth squared, then near the surface of the Earth, the force exerted by the Earth on an object is its weight, and that is equal to its mass times small g, where small g is approximately 9.81 meters per second squared, or 32.2 feet per second squared, and that is known as the Earth's surface gravitational constant.